Okay, I'm very sorry. Before we start, Javier, is Asher looking with you, or he got lost because we have changed the room?
Maybe he got lost, but he is with Bartos, so probably they will find the place.
Okay, so
in which room are you?
2.23.
Okay, I will tell him.
Okay, so sorry for this.
Yeah, so okay, so we're back with the Trans-Carpathian seminar on geometry and physics, back after the summer break. I hope the hot summer was kind to you. With the permission of today's speaker, whom I shall introduce subsequently, I'd like to take a moment to make an announcement. Sad news reached us earlier today of the untimely demise of a distinguished colleague of ours and an accomplished geometer, a quantum geometer, let's say, Jurek Lewandowski, who passed away yesterday. And I'm sure that we all have our respective private connotations and associations with Jurek and reminiscences. So I'd just like to take this moment to evoke them. But I'd also like to emphasize at this point that Jurek has throughout been, and from the onset of our activity, has been a very strong supporter of the Trans-Carpathian initiative and always trying to be actually helpful, effectively and practically helpful. So here's one to Jurek. Yeah, and as for today, we have great pleasure to host Thomas Strobl from the Institut Camille Jordan in Lyon, and currently also from the Erwin Schrödinger Institute in Vienna. Thomas is, I guess, known to everyone here in this room, not just in this room. He's a friend of the seminar and an active participant, very active participant, and also a friend and collaborator of mine, which I mentioned with gladness. So Thomas is going to take us on a trip from gauge theories to the octonionic Lie groupoid. So Thomas, the floor is yours.
Thank you very much. I would like to use this occasion. I just learned about Lewandowski. I didn't know that certainly, and I just wanted to mention that I met him at least once in a Schrödinger program many years ago, probably twice or three times somewhere. And I remember it's very enthusiastic and charismatic, and it's a big loss, I think, to all of us. Good. So I want to indeed bridge a bit the subject geometry and physics, which this seminar is about, and start with gauge theories, which are posted in both of these realms, but look at it mainly from a physical perspective, making geometry out of it, and being motivated by some questions here. In the second part of the talk, we will go to some particular problem related to the octonions, where together with Hadi Nahari, maybe I should use this here, who just finished his PhD last Tuesday, so 8 days ago, we constructed a Lie groupoid, which gives the singular foliation corresponding to the octonions in R16. There's no known Lie group generating it, and we obtain the Lie group of the minimal dimension, as we can prove. So that is the title and the plan. Now I start with gauge theories in the first part, as mentioned. I recall first the geometrical setting. This is about principal bundles, G bundle. G is a Lie group. I call the base sigma because M will often come in another place. So the space-time is sigma. And the typical fiber then is isomorphic here to the group G because the G acts freely. And in physics, the connections nabla on this principal bundle, which permit one to lift tangent vectors here to the total space, such that they project back to the given one on the bottom. These are connections. They correspond to gauge fields or the interaction fields of particles. And then if one is given an action of G on a manifold, then one can construct a so-called associated bundle. So you just need these data on a manifold M. It gives a possibly non-trivial fiber bundle F, if the principal bundle is non-trivial, whose fiber is now M, and it's called an associated bundle. And the sections of this bundle, here it's not connections, here sections, so maps which go from sigma to the total space F and then composed with the projection give the identity, they correspond to meta fields or Higgs fields. And so this describes all the fundamental interaction in the standard model of elementary particle physics, where this group G is U1 times SU2 times SU3, as most of you may know, at least if you come from physics. Now, for simplicity, we assume that P is a trivial bundle and G is a matrix Lie group. Then a connection of the principal bundle can be described globally as a one form on the base manifold sigma with values in the Lie algebra of the group G, which are now also matrices. And the section now just corresponds to a map from the base of the second bundle, the associated bundle, to the fiber M. So it's just a map from sigma to M. And gauge symmetries, they are abstractly generated by vertical automorphisms of this principal bundle P here. So vertical automorphisms means automorphisms of P such that when projected down, they give the identity. And so it's not difficult to see that if you map like a point here, then over the same base point and another point on the fiber, and you do this everywhere, then at each of these points, because this acts freely, you get a unique group element which does it, and now it depends on sigma. So these gauge transformations are now parametrized by maps from sigma to G, and they act on our fields like the gauge field A and the matter field X in the following way. So, so this is an element in this infinite dimensional group here, not to be confused with the structure group G, which I call the gauge group here, this one, this big one. So it acts on X just by pointwise pointwise action of G on the manifold M. And for the gauge field A, one has this famous transformation law. This is the joint transformation of A, or the inverse of it, plus a Maurer-Cartan form, which now in this notation is just dg. You just act on the matrix G with the Dirac differential to each entry, and then you multiply the matrix multiplication by G inverse. So now let us look at this infinitesimally. And maybe at this point I want to say, so I try to not rush over all these things, which to like at least half of us are well known, because I understand it's supposed to be also something to be understood by students. And for a student who hasn't heard this, actually that's already too fast. So I'll try to make some kind of compromise that younger people can follow. So if we want to describe these gauge transformations infinitesimally, we first look at the group action infinitesimal. It gives us a Lie algebra action, and the Lie algebra action corresponds to a map from the Lie algebra to the vector fields on M, which is a morphism of Lie algebras because the vector fields have the Lie bracket on them. And then if I now take this element in the infinite dimensional gauge group and write it near the identity as it plus epsilon and higher orders, where epsilon now is an element of smooth functions with values in the Lie algebra, then let's look first at this transformation. So the transformation of A, the infinitesimal, is d epsilon plus the commutator of A with epsilon. This can be very easily seen here. If you take G to be it plus epsilon, you just keep the orders epsilon. You get here A epsilon. This needs to be identity. Or you take here minus epsilon and here the identity. So you get the commutator A epsilon. And the dg kills the identity, so you get just d epsilon here, and this needs to be the identity. So you get this formula, which is actually the covariant derivative of this of the connection A acting on epsilon. And on x, so x was a map from sigma to M. But now we need to be a bit careful. So an infinitesimal transformation is essentially tangent, valid in the tangent vectors of M. More precisely, so it certainly depends on sigma. And to get the right bundle, you pull back Tm by the map x from sigma to M to a bundle over sigma, the fibers of which are these vectors at M attached over the image of X. And if I calculate rho G of epsilon, this epsilon was G valued function, then by rho G I get a vector field on M parameterized by sigma. And if I compose it with the map X, it precisely gives us a section here. And then since we will generalize this to different setting where we only have access to the infinitesimal gauge transformations at the moment, I decompose the Lie algebra in some basis. By the map X, I pull back local coordinates on M. Let's be them global if you like, to get n scalar fields xi. And then the above transformations read like this, where these rho ai are the components of the fundamental vector fields corresponding to these EAs. These are functions on M. We pull them back to functions on over sigma times epsilon A. So this is the transformations here, and here we just decompose this. These are the structure constants of the Lie algebra. Are there any questions up to here? Now, so we will focus precisely on this meta sector in the whole talk. One can also talk about something else, extending it to gauge fields, but I don't do this in this talk. So I first recall what is the standard sigma model. Now, sigma is our spacetime, not just the base manifold. And it's equipped with a Lorentzian metric. You can make it also Riemannian if you want. But more importantly, the manifold M is equipped with a Riemannian metric G. And then I wrote this action functional, which describes the standard sigma model in increasing abstraction. The first version is just the most maybe which physicists know about. So you get some scalar fields xi, and you give the partial derivatives of them contracted with this metric on the base. And then the contraction here, because it's a sigma model, it's not a constant, this Gij, but it depends on x, and now it's an x of sigma, and that's the volume element in our d-dimensional sigma, okay? More abstractly, one can rewrite it like this. So this Gij of sigma is just the pullback of the coefficients of Gij by the map x, and the whole term here can be rewritten like this. And now let me say something about this notation here. So if I have a map x from sigma to m, there's a tangent map, which I denote by dx, which goes from T sigma to Tm, and it's a vector bundle morphism, so it's fiber linear. So it actually corresponds to, and it identified this map with a section, the corresponding section here, to a one form on sigma, because it's linear in sigma, in the vectors over sigma, with values in Tm, but over the map x, so it's actually this pullback bundle. So this lives here. Now, if I take a metric G, it's a section of S2 of T star M over M. And now if I compose it with X, so X goes from sigma to M, and then M goes up there, so it becomes a section here. And this dx wedge star dx, now this star makes sure that this is a D form in sigma. So this was a one form here in sigma. Now it becomes a D form in sigma. And then we get two elements in X star Tm, and I can contract the two, and I get something which is just a D form on sigma, and I can integrate over it. Okay, so now we want to gauge this theory, and the standard way of doing so is that there's a Lie group G which acts by isometries on the target manifold, which now is equipped with a metric G. So in particular, if you look at that, this implies an infinitesimal invariance of the metric G with respect to the fundamental vector fields generating this group action or Lie algebra action. So here's, I recall what was this rho G. So given any element, it gives you a vector field on M, and these vector fields are killing vector fields. So these vector fields under the Lie derivative annihilate G. And then the gauged standard sigma model in the notation from before. Is there a question?
No.
Okay. It's just replacing what we had here before dx by the covariant derivatives on x, which take this form. So this is again living in the right space with the same argument as before for a variation of x. So this is called minimal coupling. So the coupling between x and a only arrives by means of these covariant derivatives. And the covariant derivatives now use a connection on the bundle F. And this connection is also induced by nabla. So I can go back here. So we have this associated bundle. We have here a connection. And it turns out that this connection induces a connection here. Remember that this connection was given by a one form A here, and we had the action of G on M, which was used as rho sub G, so that the covariant derivative in the end of the day turns out to be just like this. It's then canonically given. And then this is now gauge invariance. What does it mean? So if I use the gauge transformations written in the very beginning of X and G under any change of the gauge group, then the action functional stays strictly invariant, or infinitesimally we have delta epsilon S for any epsilon in here is 0, where these infinitesimal transformations are just recalled here again in the index-free notation and in the index notation. And note here that here we have structure constants. So that's very important because we now want to relax this point precisely. So,
May I ask a question?
sure.
Yes, so can we remove this gauging by passing to the ATIA algebroid of this principal bundle? Yes.
Now we can remove pointwise gauging.
Oh, you
but
can,
this
if you
will-
want, if you want, you can certainly start just here, right? So what I wrote is the gauge standard sigma-mod is what you get if you discuss the kinetic term for sections S here. So you're right. I was just like, I came from these bundles here. I then said, let them be trivial. And then actually I can forget about the geometry up there, just have one forms here and functions here. And they transform under something. And then I recall what is the standard sigma model. That's such a functional. And if I want to gauge isometries, then you just get this replacement, you get the invariant term, which certainly if you had started geometrically on the associated bundle and the principal bundle, you get on the principal bundle the Young-Mills term, and the kinetic term for, say, the Higgs field is precisely of this form, where then the manifold M is just a vector space in the case of the Higgs field. C2, if I remember.
Yeah, so yeah, this is because you use gauge group, not just the group action on the tangent bundle. Yeah, so this group element depends on the point. Yeah.
Sorry?
Yeah.
I didn't hear the last phrase.
Because I think because you use representative of the connection as a one form on sigma.
Yeah.
No, but you can do.
Okay, but this is a standard thing. I just want to recall this. Let the students not be confused by these discussions. I would propose to continue now. I took a picture of this, which I don't want. Let's throw it away.
Thomas, if I can make a remark, maybe this clarifies things a little bit. So in general, what you can do.
No, but Kalin, I think we should not go into this. This is really a
Okay.
very standard thing, and I just, because of how I will continue, I wanted to start with this gauging, because for the non-trivial gaugings it will be more difficult. And yes, one can give a whole lecture just about what I said. I agree.
So,
but
Thomas, just maybe a quick question. Namely, you were discussing this minimal coupling. And for example, if you consider not metric terms, but also the topological terms, more general scenarios can happen.
absolutely.
Have you considered non-invariant tensors like metric tensors, more general invariance conditions for the metric? Because in those topological terms, you can have non-invariant couplings and still you end up with an equivariant structure, and which is something on top of the most basic invariance condition.
Yeah.
So understand that this can also happen.
In two dimensions, I did this, and it led to generalized geometry, but it's another talk. Okay.
Just point.
Okay. So why I took the perspective of this gauging and the components and this local gauge field, which for trivial bundle become global, is because now we can have a different perspective. So we have again our manifold M, and before we had group orbits, and they needed to be isometries. Now let's assume we have just some leaves of varying dimensions generated by some vector fields on M. So these VA are generators of such leaves. Let them be involutive. So there are some structure functions, C, A, B, C, and this is the Lie bracket of vector fields. And then you look at the C infinity module generated by these vector fields, usually over compact support. And now this is close with respect to the Lie bracket. It's here globally finitely generated. So it gives an example of what is called a singular foliation. So let us take a singular foliation. It's now described by these structure functions, where I need to remark that since these vector fields are at a given point not linearly required to be linearly independent, these structure functions a priori are not unique, but we choose some. Okay, we choose some which do the job. And now we want to see, can we gauge these orbits instead of the orbits of, or these leaves instead of the orbits of a group of isometries. And I start in a very naive way. So I again have these n scalar fields. I have, if I had a Lie algebra of dimension r, I would have this R1 forms on sigma, but now this Lie algebra will disappear. And for the infinitesimal gauge symmetries, we keep the same thing here, where now these are not the generators of the Lie algebra action, but we just take the generators of this singular foliation. And then we make an ansatz, which can be actually more general here at this level. The essential point is that we permit a dx term so A is a one form, this is a one form, this is a one form, but we can add also something proportional to d-axis, is also one form. So it works in any dimension, and which it just turns out to be convenient to take the covariant derivative here that rescales these parameters, which then become the structure function CABC. So let us try this. And where these gamma now are new structure functions, which entered the game in this way. And now let us still keep the minimal coupling. So we have this dxa, dax as before essentially, or as written precisely here. And now the statement which we found with Alexei Kotov was that this is gauge invariant under these infinitesimal epsilons if and only if the metric, the Lie derivative along generators, is not necessarily zero, but satisfies such a condition where the gamma ABs now are one forms corresponding to whose components are gamma ABI. And so now there's different ways of reading what this means and reinterpreting the physics formulas in purely geometric terms. So the original way we chose with Alexei was the following. So construct an almost Lie algebroid over M just by taking the trivial bundle M times RR, take sections in it, like we have R sections in it, which are global sections here, just maps to RR from M. And the map rho, we just define in this way. So the image of sections here give the vector fields of the singular foliation. And now remember that we had to choose CABCs. So, and they are now used to define a bracket here, which is an almost Lie bracket on the sections of E. And here now these are linearly independent. So here this choice really matters. But for any choice, we can do this. So in the construction of these data, there's some ambiguity. But let's fix it here at this stage. And then reinterpret this these coefficients gamma as coming from a normal connection on the bundle E, which has the usual form. So these are connection one forms, and this usual formula, these are the coefficients. Now, the first step for this geometrization is to interpret our gauge fields, which we had was mapped sigma to M as before, and now the one forms are not Lie algebra valued, but they take values in E. Okay, I drop now in my words always the pullback bundle by X, so it's a section over sigma, but it's understood. So I just say with values in E. And these two data together is the same thing as a vector bundle morphism from T sigma to the vector bundle E. So the base map is the map X, and again, it's fiber linear, so it's a one form on sigma with values in E. That's the same thing. So we can say actually that we have that the fields are such vector bundle morphisms, and the functional is this, the under quotation mark covariant derivatives at this level under quotation marks, because at least here we do not attempt to give a global interpretation, looks as such. And here I use this notation underlined sometimes with the X to make it clear, where I say if I have a map rho from E to Tm, and I have a map X from sigma to M, the base of these two bundles, it induces a map for the pullback bundles. And that's the one I need here. So A was taking values in X, is a one form taking values in X star E. And now applying this, it takes values in X star Tm, and this indeed becomes a one form with values in X star Tm, and I can construct this. And I will not go into all, I will not go in, let me just finish this first. I will not go into all details how to continue working. So, but now you can, the theorem is that this is invariant under appropriately defined gauge transformations, which now can be done without indices, if the metric G satisfies a very natural condition. And as mentioned, I will not go into all details, so one needs to define an equivariant derivative induced by normal covariant derivative on E. And the gauge transformation, so here's like the torsion of this E connection plays a role, which replaces the structure functions of the almost Lie algebroid. This is a tensor. Structure functions of a Lie algebroid or almost Lie algebroid are not. So that are the global formulas, and then this becomes a theorem. And one can relax it, as maybe said, indicated before. You can start with anything which goes like d epsilon, epsilon a, and epsilon dx with arbitrary coefficient. Require that that function is invariant. You find it has to be of this form, and thus permits this reinterpretation. Now, the drawback of this formulation is that it uses some auxiliary data which are not unique, given this original singular foliation on M. So with Hadi, we reformulated it in a different way, just using the singular foliation on M. And then the condition equivalent to that condition, but not using those auxiliary data, is that for all vector fields in this C infinity module of vector fields, satisfy that if I have the leader with respect to one of them of the metric, I end up in the following symmetric. So this is a symmetric tensor. It's a symmetric tensor block of arbitrary one forms and G flat of the singular foliation, where G flat is the musical isomorphism, mapping vectors to covectors. And these were vector fields, so this become one forms. And we called a singular foliation on a Riemannian manifold satisfying this condition star prime, a singular Riemannian foliation. And since there will be another one in the game, we stressed that this is a module of functions, so it's a module SRF. Was there a question?
So what you call singular Riemannian foliation?
Sorry?
What you call singular Riemannian foliation?
Yes. So you take a singular foliation in the technical term, which has the properties I mentioned before, but it's locally finitely generated, is sufficient. We
What
don't.
is the compatibility with the metric?
Red rectangle.
Red rectangle, czerwona ramka.
Yeah.
Ja nie rozumiem.
That's the main condition, precisely. There's a nice way of seeing all this in the Hamiltonian language, where.
Sorry, Thomas, may I ask a basic question?
Let me just answer, let me make this remark to Janusz. You see, like a singular, like vector fields on M, one can view as fiber linear functions on the cotangent bundle over M. They generate, these vector fields generate over this cotangent bundle an ideal, which is a Poisson subalgebra. So we would call it coisotropic subalgebra. And then this condition becomes very simple. You know, the metric G defines a Hamiltonian on the cotangent bundle. And the statement here is equivalent to saying that this Hamiltonian preserves this ideal generated by F. So that's a very natural condition. On this Hamiltonian level, it's like the most natural it can be. But also here you see it's defined in a unique way and also in some sense very natural. There was Karin, you asked the question?
Yes, I just wanted to ask what's the relation between this notion of singular Riemannian foliation and the notion of Riemannian foliation used by Molino in the book.
Precisely, that will be my second part of the talk. We will precisely.
So if your foliation is regular, so this is the same as the standard Riemannian foliation.
Yes.
Okay, thanks.
For example, if it's regular, they're equivalent. Let us give 3 examples. First of all, if we have killing vectors generating such a singular foliation, then this gives an example. Note that the killing vectors from a vector space but not a module. So even for killing vectors, V being a killing vector, but then permitting coefficients within killing vectors which are functions, you get such terms. You can just easily calculate. So even the singular foliation of killing vector fields give this equation. Then a very orthogonal example is a Riemannian submersion. So if you have M and you have a fibration over Q, and you have M and Q both being equipped with a Riemannian metric, such that Q is a Riemannian submersion, which means that the metric here can be obtained from the metric at any point over the base point orthogonal to the leaf. And for the singular foliation, we just take the vertical vector fields. That means those vector fields which are mapped to 0 by the tangent map. So that's another example, which is certainly extremely far away from isometries, because the metric on the leaves can be arbitrary. Just the orthogonal ones, they need to be invariant, so as to come from the base. And as we proved with Alexei, the base of a proper Riemannian Lie groupoid, a la Rui Fernandez and Matias Del Hoyo, they also give an example, more intricate example. So this seems like a lot more than isometries. But however, there's a question. Can we really describe new physics by this? I was very convinced about this because we found examples where this connection nabla had a curvature and constructed this curved Young-Mills-Higgs gauge theories where we add the kinetic term for the Young-Mills fields. However, I noticed relatively soon that in that example I gave, one kind of can get rid of this and describe it equivalently by just a U1 gauge theory there. So the question is there, can we really describe physics which we cannot describe with an ordinary gauge theory? And that could happen in some tricky ways. And the goal of this first part of the talk is to just translate this kind of physics question into some clear mathematical questions. And there will be 2 approaches for this. And the first one are Witten transformations. So they have this name because I received an email where this was proposed to show that this example I gave in this curved Young-Mills-Higgs case is equivalent to a normal U1 example, which I had found independently before, but I didn't think of it in this way, namely that you make a field redefinition of the gauge field A by something along dx. So the idea here is that field redefinitions of my action functional will give equivalent gauge theories. And in particular, these Witten transformations, they don't change X, but it just shift the field A by adding something of this sort. It's lambda times covariant derivative. For some lambda, which is a map from Tm to E, lambda bar is this map. And to have invertibility of the change of variables in the field theory, we need that such a map, you see here's lambda inside. In this dx, there is dAx is dx minus rho A. So you get lambda rho, it minus lambda rho on A, and that needs to be invertible. So any lambda such that this is invertible gives such a valid field definition. And let us apply it now to the covariant derivatives which enter the action function. So,
sorry, Thomas, but what's the geometry behind this transformation? I mean, A can be thought of as a one term, but it's actually some geometric structure on the, let's say, the principal bundle if we're in the group case. What does it even mean, this transformation of the gauge field geometrically, in terms of the Eresman connection on P? What is it?
No, but there's no principal bundle here, right? There are these. There's more general bundles, but I didn't want to talk about this here. So there are different ways of thinking about it. Here at the moment, everything corresponds to trivial bundles, and the objects are well defined. X was a map from sigma to M, and A was a one form on sigma with values in X star E. So that's all well defined, and I have a functional depending on these data that's well defined completely mathematically, and I just want to perform such a transformation. Certainly, I can translate it to more complicated bundle questions, and they become again interesting and to be studied later. But here, everything is at least well defined, and it's a simple calculation which I want to show you. So let us look what happens to this dAx, call it covariant derivative or not. So I now replace A by A tilde. Recall that A tilde was just a shift in A. So one term is just, will reproduce the old one, so this dAx. And then what? And then I get this extra term composed with rho. So I get rho circle lambda acting on dAx. And now you see that, okay, I can combine these two into a new transformation, it minus rho lambda, and the condition star implies that this is not any endomorphism of Tm, but it's one which is invertible, so it's in GL of Tm. And now it means, if you just look at it, so this dA tilde of X is just a matrix or endomorphism times dAx. You plug it back into the action, and you see that you get effectively a new metric, G tilde, which is of this form. And now the covariant derivative with respect to A tilde in the game. So we see that any lambdas of this sort, which are in GL, map G tilde to G, and now it could very well be that this doesn't have isometries, but maybe this does. And in very simple examples, suppose that rho is the identity map, the singular foliation are all vector fields, then certainly with such a transformation, I can make it any metric flat. In that case, here, however, we have a transformation only identity minus something inside in the direction of the foliation. And there's now one simple corollary of typical mathematical physics nature, that given a singular Riemannian modular singular Riemannian foliation, then if I replace G by G tilde construct as above, it has to be again a modular singular Riemannian foliation because it's still a gauge theory. And there was gauge theory if and only if this condition is true. So without calculation, this has to again be a singular Riemannian foliation. So it's a way of constructing new ones.
May I ask some stupid questions? So this formula for lambda looks a bit like the formula used when you construct a homotopy equivalence between chain complexes. So is it possible to use some sort of homological perturbation theory where you treat this row composed lambda as small in some sense? Have you thought about that?
No, I haven't.
Okay. Okay.
But usually
Sorry.
with modules, this is kind of tricky with these homotopies.
It can be done for graded modules, for example. It's very standard in homological algebra. So I have a feeling
but usually I just remember from our paper with about this Lie infinity algebroids. So there it did not work with homotopies because of the fact that we have modules over functions.
I think the basic idea is somehow trivial. So because this lambda is somehow invertible, when you compute its inverse, you can expand in this inverse of identity minus row composed lambda can be expanded as a power series into powers of row composed lambda.
Yeah.
Typically, that power series terminates. Okay, I don't know if that happens in this case, and you can play along here. So it's
why should it terminate here?
here probably it doesn't, but in the graded case, you generally put homological conditions so it does.
No,
But
but it's a valid question what you say. I didn't have this association, but
I mean, somehow, if you see this formula, it's somehow
I understand.
Standard idea. Yeah. Okay.
Mm-hmm.
Anyway, it's a deviation.
Yeah. Thank you. So we also observed that the standard sigma model gauged with respect to this and this are physically equivalent on a classical level. Otherwise, we can get determinants of the change of variables. And this gives us now the first math question about this question of physics. Is it possible that for every module SRF, MFG, one can find a Witten transformation where G goes to G tilde such that the same singular foliation from the beginning can be generated by killing vector fields of G tilde? And we were not able to answer this question yet. So this question is still open, but we have at least a clear mathematical question, which says if we can answer this with no, then there would be theories which, at least under Witten transformation, cannot be transformed into one of a standard gauge theory. And I think at this moment, we need to take a break.
Yeah, I think that this question is somehow related to, anyway, to what I said before.
Right.
Yeah.
Okay, so now there is 15 minutes break.
Okay. So at 15:18?
Yeah.
Okay. Yes. Okay, then I need to. Sorry, I need to find this now. Where is it?
You have to.
Share. Advanced. Doc. Share. Okay.
So it is almost okay, but instead of the slides, we see the. Great. Now it's visible.
Yeah.
We can continue.
So you see that these transformations change only the metric, and in particular cannot change the dimension of M. But it's also quite clear that in principle there can be theories with different dimensions of M, like different number of scalar fields which are effectively equivalent if you add some directions which are just pure gauge. And so I was thinking how to incorporate this, and I think that the right notion is this Morita equivalences, which we're studying with Hadi. And so let me start with a definition. Let two module singular Riemannian foliations, we call them Morita equivalent. In fact, n Morita equivalent, where n is an integer, non-negative integer. If there exists such a diagram, where here are the two module Riemannian singular foliations, and here is a Riemannian manifold, with the following properties. Both these maps are surjective submersions, and they are in fact Riemannian submersions. We had that before. And now this n enters here, that in the saying that the fibers of this, so if I fix a point here and then look at the fibers up here, they are n connected. Okay, so there's a different level of strictness on what we require from these submersions. So the higher m, the more complicated it may be to construct it. And the second thing is that the pullback foliation should agree on here, which it's like just to get the idea. So you look at all vector fields. So like, for example, pi1 of f1, pi1 inverse of f1, it's all vector fields here, which project into here. No, it's actually generators like this. So it's even more tricky, because then you need to generate it, and up there you can take functions arbitrarily. So in particular, there will be vertical vector fields which are in the pullback here. So you add essentially on M to these vector fields, you add vertical vector fields. And here you add other vertical vector fields. But in the end, here you get an induced, you prove that you get an induced modular Riemannian singular foliation, and they have to be the same. Okay, so that is a definition. And we defined without the first Morita equivalents of model SRFs, and they just correspond to n equals 0. So now this is a refinement. And now we call that I define now a definition of an equivalence of gauged sigma models of the form we had before. So remember that they were vector bundle morphisms from T sigma to some vector bundle E over M. Now this E over M can be different, and M can have different dimensions also. We call them equivalent if after some field definitions, you can write one of the two functionals as precisely the original functional S1 with the fields after field definitions being those from this one, plus, and I wrote it a bit symbolically, plus fields which are enter quadratical in action, so that if you make a variation of these terms, B doesn't appear here. If you vary with respect to B, you get as an equation of motion, as an Euler-Lagrange equation, you get B equals 0. So no physicist would doubt that we can just drop these terms. It's, however, slightly subtle. And
sorry, is this mathematically, this is some kind of convexity requirement, right, on the action SFI? Am I correct?
I just require, I call these two equivalent if after field definitions I can drop also quadratic terms.
Yeah, I understand, but it's somehow physicist's way of thinking. I mean, mathematically, you are essentially requiring that. Oh, I see. You seem to be requiring some kind of convexity. If you think in terms of independent of the field definition, if you think in as this action as this action functional as a function of some.
Okay, what you're saying is one can generalize this. Yeah, sure.
Yeah.
Sure. But it's sufficient here, so.
Okay.
Purpose here. So, so in other words, these are equivalent up to total squares without derivatives. And then also this now permits to change the dimension of M. And the theorem we have is that two standard sigma models gauged with respect to Morita equivalent M SRFs are equivalent in the above sense. And I wanted to give a proof of this, but I noticed that it takes some time and like change of variables and so on, and I need to argue with a field bind and it's some calculation of 2 or 3 pages, which I cannot do here. So, but that is the result, and there is still like some footnote. Even if the two sigma models are Morita equivalent, it doesn't mean necessarily that they have isomorphic solution spaces. And this is essentially related to large gauge transformations. And we integrate out only the flow of something. So we have only the gauge group a priori quotient by the gauge group connected to the identity of these infinitesimal ones. And then you can get some homotopy classes which you don't see after which you don't see in the squares. The square can get rid of some field which has homotopy classes, which are gauge invariant objects. And so you don't get isomorphic solution space in general. But our conjecture is that this changes if we ask the Morita equivalent MSRS as target, where D is the dimension of sigma. And we proved it for spheres.
So let me just make sure I understand, Thomas. So you mean isomorphic moduli spaces or solution spaces? Because these
right.
So
yeah, solution model or gauge symmetry is certainly not smooth, which is a singular space, but then as an isomorphism of what it is. So that's a bit a tricky question, and but it's moduli spaces, yes.
Moduli spaces, okay.
Yeah, absolutely. You get rid of some symmetries also.
Okay, thank you. So, and you said the issue is a bit like in Teichmüller theory. So the issue is the large gauge transformation somehow, morally speaking.
I think so. Yeah, I think there's some choice. We just stick to the gauge, factoring out. We know the infinitesimal gauge symmetries at this level.
Yeah.
And we take just the group generated by those, but this is by definition connected. And then one can construct examples even with ordinary gauge theories, like where you use sigma equal to S1 and the group being either U1 or R, and you get different moduli spaces, even if it's up to homotopy.
So
you take that at 0, you still get different moduli spaces.
Somehow the intuition is that this is a topological issue, so that's why you can expect it to be solved if you require this Morita equivalence.
Yes, we believe that, and we proved it for this case in some way.
Thank you. Thank you.
So I also promised now a second math question, and now again to see if I can describe something which one cannot describe by standard gauge theories. In this perspective, it's is there any MSRF that is not the Morita equivalent to a homogeneous one, which means it can be a completely different manifold dimension with a completely different metric, another foliation, but it is the Morita equivalent, and this one would have a singular foliation generated by killing vectors of that metric. So that's unfortunately quite a tricky question, because these Morita equivalences, they are not easy to construct if you have given two MSRFs. And but okay, we still will make some statements here. And so the summary is to find a standard sigma model gauge with respect to these more general gauge symmetries cannot be described equivalently by a standard gauge theory if we can assure that this singular Riemannian foliation is not Witten equivalent or de Morita equivalent to homogeneous SRF, where D is again the dimension of sigma. Okay, so that is like what I promised, these two mathematical questions in which we said, okay, new physics. So we have this Witten transformation and the de Morita equivalence to homogeneous ones.
Thomas.
And the question is open, so we don't know the general answer.
Can I intervene with a single comment? I mean, so here the notion of gauging is used in a particular sense. I mean, if you think of gauging as reduction by the action of the gauge group, so passing to the Orbi space of the gauge group from the original configuration space, then you have, strictly speaking, only considered a single, so to speak, a single sector of the gauge field theory, and a very special one in which the gauge field is a global one. So it would correspond to, in the standard classical gauging procedure, to a trivial gauge bundle, to a trivial principal bundle.
What I discussed
And
here,
of
yes.
course, you'd have to refine it as we do it, right? But then I'm not sure if this Witten's trick, another Witten's trick, which can be written just like that for the trivial bundle, if it could even be made sense of in the presence of the sheaf description of, so locally it would be the same thing, but you'd have to glue the local descriptions with precision mappings of the, right? Okay. So it's a very special.
Okay, there can be obstructions if one asks more. I restrict it here to the standard sigma model. There's a similar question for the curved Young-Mills-Higgs gauge theories, which is a deformation of the Young-Mills theory with Higgs fields together, which doesn't have a structure group, but only a structure groupoid. And some equivalences on this level may not live to equivalence up there. Something can be a Morita equivalence for MGs, but if you have built the whole tower of additional data unit, maybe it doesn't work there. So there are many layers to this. And this is, I try to focus on something specific. This is something which is a clear, clearly well-defined question for a standard sigma model. I can gauge it without isometries. I ask, can I maybe not find an equivalent, physical equivalent one, which is just a standard one, which describes the same physics? And this is a mathematical reformulation. One needs to study Witten equivalences and de Morita equivalences and find one example where it's not equivalent to a homogeneous one with isometries. So that's the question. And that is also what led us to look at the second part of the talk, namely the...
Still ask a question. So a definition can stand everything, but do you have a nice non-trivial examples of Morita equivalent singular Riemannian foliation?
What is the question again?
I don't know. Do you have nice non-trivial examples of Morita equivalent singular Riemannian foliation?
Okay, but I think this is related to what I'm going to say now. So I'm talking a bit about the motivation, why we look at these octonions, and what Karin also mentioned, there's this classical notion of single Riemannian foliations, and there's a question, how does it compare to our notion? And you will soon, I think, find an answer to your question. Let us proceed a bit. If not, please repeat your question then. So by some colleague, we were made aware of the fact that there is a well-known singular Riemannian foliation in the sense of Molino, which is non-homogeneous. And so that is why we looked at it. So we were told that this is an example, and so we should look at it or we wanted to look at it. So I ran around asking for such examples, and this was what I was given. So for this, first I need to tell you what Molino's definition is. So in the Molino sense, it does not deal with a singular foliation in the module sense, but just with its leaves. That's why nowadays it's no more considered as maybe the right notion for what concerns singular foliations. And then if I have a singular foliation, but only a leaf decomposition and only a Riemannian manifold MG, then it is a geometric SRF. So geometric comes from us. We called it like this because it's only about the leaves, not the modules. If every geodesic which meets one leaf orthogonally stays orthogonal to all the leaf it meets. So here's a very simple example. Take R2, take concentric circles, and the geodesic is a straight line. To be orthogonal to one of the circles, it needs to go through the origin and stays orthogonal to all of them. certainly these isometries, and this will be such an example. It's a simple example, but not the only one. Actually, this octonionic Hopf foliation R16 is an example which satisfies this. Now, the other thing is, how do these two relate, modular and geometric SRFs? And we proved that we have this one direction. If you have a modular SRF, we always get a geometric one. And the question now is, what about the inverse direction? And this question has several layers. For example, here we have given only leaves. There can be several modules generating the same leaves. And then usually it's not for all modules. So the real question is, given a geometric singular foliation, the leaves here, does there exist any module F such that with the leaf decomposition L such that now together this is a module SRF? So that's an important question. To which we will find a partial answer in this talk.
But sorry, may I just again ask something? Sorry for pestering you with so many questions. So somehow the traditional point of view is that what matters is holonomy groupoid of the foliation. This is ultimately what deals with this all these issues of how you present a foliation. There are many ways to to describe a foliation, through modules, through leaves, through singular leaves.
They're not equivalent. The leaves and the modules are not equivalent.
Of course, right. But to deal with this ambiguity, usually, I mean, the traditional point of view, I think for the past 20 years or so, has been to look at the foliation, the holonomy groupoid of the foliation that you are considering. Have you thought about that at all?
In principle, yes, but not in much detail yet. But we have some other things we thought about, so I will talk about those.
Okay.
It's certainly a good point, and
okay.
we are discussing this also. So let us be now more specific in this question and separate them in several ones. So given this R16, which where we have this single octonionic Hopf foliation, is there a singular foliation in the sense of a module of submodule of the module of vector fields such that this becomes a singular foliation? The second question, does there exist such, may possibly different F, such that R16 together with the standard metric and this F is a module SRF? And the third question, can we prove that either as a GSRF or as an MSRF, it is not Morita equivalent to homogeneous GSRF or MSRF? And we will get partial answers to these questions, but as a spoiler, we will not find an example of a non-homogeneous MSRF, okay? That is just what happened. However, we have still some interesting things. We get some answers to the questions, we get full answers to Q1 and some answers to Q2 and Q3. Some are still open, I will tell you. And what is very interesting, we think, is we found a Lie groupoid generating the singular Riemannian foliation. That's like the next best thing after group action on a manifold to find a Lie groupoid. And we can prove that it has the minimal dimension generating these orbits. So let me go into this. So first we need to talk about the Hopf fibrations and singular Hopf foliations. I again try to be pedagogic. However, I'm not sure if let me still start in a normal way. Okay, so there are 4 division algebras, R, C, H, so the real numbers, complex numbers, the quaternions and the octonions. 3 of them are associative, and they are the 4 norm division algebras. And first we do the Hopf fibrations and the singular Hopf foliations for the first 3 of them. So look at the associative division algebras and look at the elements which have norm 1. So actually, this is a Lie group, and I listed which Lie group it is for the 3 cases here. So like in complex numbers, like complex number of unit 1 is a circle. Actually, complex quaternions are the group SU2. And in the case of R, it's a bit stupid. You just get +1, -1. So 0 sphere, 2 points. The group Z2. Now take any of these elements in this group and act on a couple of xy in A2, which is R2, C2, or H2. And this C2 is R4, and H2 then is R16. Is it right? 4 times 2? No, 4 times 2 is not 16, it's 8. Okay. So this gives an action, and actually it turns out that this action is isometric. So this UA is in the isometries of the standard metric on this A2. So we get an action groupoid here. We get a group action, which also can be viewed as an action groupoid, but we get a group action by isometries. And as a simple corollary is that in this way we get an MSRF in all 3 cases. So this is over A2, for example, for quaternions, it's R8, I hope. Okay, now what are the leaves of these singular foliation? First, always we have the origin. Just look at this group action. If I put 0, 0 here, it remains 0, 0. So there's always the origin as one leaf. And the other leaves are actually isomorphic to these groups because we have a principal bundle for the other ones. So let SA be A2 intersected with a sphere of radius R, not a positive radius R. And then we get a principal bundle. I don't go into the details, but I think it's kind of nice for students to see this in each case. So here's R, C, and H as the associative norm division algebra. Then this space SA, which is just spheres of some non-vanishing radius in here, is S1, S3, and S7. So this was an R8 unit sphere, for example, is an S7. Then this group, since we have a principal bundle, it's also diffeomorphic to a generic leaf or to any leaf of this spheres. Here is just 2 points. Here it's S1, and here it's S3. And the base is now, so here we just take antipodal identification of this S1. We again get an S1. Here, this is the famous Hopf vibration, the Hopf vibration of S3 over S2 with fibers S1. And the one for the quaternions we obtain in this fashion is from S7 to S4 with fibers S3. There's also one funny thing is that the total space of the previous one gives the fibers of the next one. And in fact, this continues also for the octonionic Hopf vibration. So the octonionic one, the fiber is what is the total space for the quaternions. And unit sphere in R16 is S15 and the base is in S8. So there is such a Hopf vibration, which however cannot be constructed by isometries as in the other cases. And I just for completeness, I now look at the single Hopf leaf decompositions for each of these cases. So here the leaves were S0, which were points, or no, not S0, the origin or points. Here the origin is in each case, and here we get leaves S1, S3, S7. The first 3 come from an isometric action on these spaces, whereas R16 is not generated in this way. And the existence of a singular foliation in a module sense in the modern sense also, is easily answered. Here we have this killing vector fields generating this singular foliation. We have an action groupoid. Whereas here it was the question one we posed: can we find a singular foliation in the modern sense to give the correct leaf decomposition? Then is it a geometric singular Riemannian foliation? This is true in all of the cases. Here it was precisely the point which draw attention to this example. Is it a module one in all these cases? Yes, here's question 2. And then the Morita equivalent to homogeneous ones is here Q3. And if the answer to this question is yes, then we have here also Q3. And while we could just construct it that simply for all these cases, for octonions, we need a different construction. And this is now explained here. This construction works for all of these, so I leave it in general. It's just an alternative construction in that cases, but this one works also for the octonions. So look just at line. So you have D2, think of like R2, and you have a line here, which is like y is equal to mx. And now you just do the same thing for x, and this is the multiplication in the corresponding division algebra. Add to it the line with infinite slope. M is called the slope now, in generalization of the slope in R2. And intersect this with a sphere, then you get the Hopf vibrations. So if you take these lines, intersect with a unit sphere or another radius sphere, then you have this intersection, and this for the octonions is a 7 sphere. For R2, it's just 2 points, as you mentioned before. But in the other case, it becomes connected in the high dimension one. It's just so these are the leaves. So the intersection with all spheres for arbitrary positive radius and all slopes, even infinity, and adding the origin to this gives this singular Hopf leaf decompositions, which for D equal to O we call like this. Okay, so that's a construction. And now we want to address the question 1. Can we find a module generating it? For this, we have the following lemma, which is quite interesting. So a vector field in O2, we can describe as an O2 valued function on O2. So we have UV, each U is a function on O2. And so these are elements in O, but each element is a function of X and Y in O2. And they are, a vector field is tangent to this single octonionic Hopf foliation, or you can take any other element from D, if and only if it satisfies these equations. And these equations look very innocent, but to solve it for quaternions, octonions, and in particular for octonions, it's really tricky because you need to solve it. It looks like a linear system for U and V, but these are functions of X, and the coefficients are elements in a ring, and that's quite tricky. But one thing one can prove easily with this is kind of a very nice proof that UV cannot be linear in X and Y. And the proof actually is just reduced to non-associativity of the octonions. So it's a simple proof, like half a page, and because O is non-associative, U and V cannot be linear in this case. And there's a simple corollary of this, namely saying that this cannot be generated by isometries, because isometries of R16 or of any Rn with the standard metric, which leave the origin fixed, are rotations, and infinitesimally, the general vector fields vanish at the origin linearly. So It cannot be true. And this is a famous fact which we proved like this. So in one of the papers, for example, they looked at all possible homogeneous spaces with fibers S7 and then just ruled out that they cannot come here in this case from any isometries of R16. So this is one of the things we find. And now much more complicated to see thing is that all the vector fields tangent to this single octonionic Hopf leaf decomposition can be generated by 16 vector fields. So A and B are octonions. Wherever you see here, it's the octonionic multiplication. A and B are constants, but you generate over O. And now, originally we mentioned always the infinity function actually should be even compact here. But there's another way, a sheaf-like definition where we can ask us all these questions equally for real analytic or polynomial singular foliations. And the proof uses a computer program, because to solve these equations, they are like 8 + 1, 9 equations in 16 functions on R16. So these are really complicated, and to find all solutions in the polynomial setting, one uses some Riemannian basis, and this just by hand, this just becomes impossible. But with these programs, we can do it. Then one can use flatness theorems to go from the polynomial setting to real analytic and smooth. So the answer to the first question is yes, there is a singular foliation. Actually, this one is maximal on all of them. So you can find others which are like vanishing to 5th order, say, but still have the same leaves. But we have also the maximal one here because this is all vector fields are generated by those. Okay, so we found an answer to the question 1. What's the question?
Yeah, I mean, so if I understand correctly the theorem, you are stating that the result on the system of generators does not depend on the choice of regularity here. So for compactly supported smooth functions or analytic or polynomial, you get the same generators.
Yeah, the generators are all the same.
Okay.
So the generators do not have to have compact support, for example, here, but then they're multiplied by something with compact support. So they give
as a module, yeah, okay.
They give vector fields with compact support, but the generators are not required to have compact support. That's an important issue. Note that they are quadratic. You see they are quadratic x, x, y. So they're all quadratic.
Regularity is for the base ring, and here you are looking at a module of vector fields. Okay. Yeah. Thank you.
And yeah, so they couldn't be linear, we said, but they are quadratic, and they are
okay.
Certainly another F can have much higher vanishing order at the origin, can be also singular foliation with same leaves.
Thanks.
But here's the maximal one. So what about the question A2, which was, is it a module SRF? And we can answer this question with a no for the real analytic setting. For the smooth, it's still an open question, and we don't know how to solve it, because there can be functions which vanishes to all orders, so it doesn't, the Taylor expansion doesn't help. But let us now assume it's real analytic, and then we can prove easily it's not a module SRF. And the proof goes relatively easy. Take a non-zero vector field inside this singular foliation F, and let it, so it doesn't need to be the maximal one, but we know that the maximal one has vector fields vanishing to order 2 at least, or higher. So this F can have another K as an order, and take a vector field which is vanishing of this minimal order. Certainly you can multiply by a function which vanishes to order 10, and then you get k plus 10. But let's take one which is of this minimal vanishing order of f. And k is at least 2, vanishing at the origin. Now, it's much, I think, a very simple calculation. The leader of the standard metric is, I don't know if we need a factor of 2 maybe, but doesn't matter. The components of vi, the round differential, symmetric tensor product dxi. I chose capital Xi because we have x and y before. And it's not to be confused with scalar fields. Here are no scalar fields anymore. Everything is just geometry. And now, because this vanishes of order k, its derivative vanishes of order k minus 1. On the right-hand side, I think I get smooth one forms, and this k was the minimal vanishing order of f. So this vanishes of order at least k. And now we get a contradiction. We would need a one form here, which is single at the origin. So either the vector field v is 0, or we have a counterexample because we want some single foliation which has the right orbits. So yeah, that's kind of unfortunately. So it's even a very simple proof. However, we do not know how to adapt the proof for smooth, and this is still an open question. But we don't have, that's the main reason why this did not give an example for non-standard gauging. Okay, now what about this groupoid? I still have 10 minutes. So let me sketch how it works. So first we need to define some kind of strange function, which is a function O4, but I will split it in O2 times O2, where this will be the base of the groupoid, and we will see in a second. And it's this strange square root, where in here, for example, the octonions are multiplied. And one can prove it's well defined. One can prove that this is always positive, but can be 0 also. Now, the groupoid itself is, as a manifold, a subset of O2 of 2. Namely, if you take away all points in here where this function lambda vanishes. And so a groupoid element is now quadruple of elements which are octonions, and our base is still O2, which is also R16. And now we need to define the structure maps. So let me change the page. The source map is just the projection to the first x and y, whereas the target map is quite some beast. It contains a particular 1 over lambda, and that explains why we need lambda non-zero. Now, the multiplication, on the other hand, is funny. It's almost addition of these f and g's. Just there's a rescaling by these lambdas again, giving it a funny twist. So for those who don't know what groupoids are, so groupoids are essentially arrows, like morphisms in some sense, of elements in O2. So xy is an element in O2, and they can be composed. They have a source and a target, so they map one thing to another thing, but it can be mapped in different ways with different g's, which have the same source and target. But to compose them, we need that the target of this one is equal to the source of the subsequent one. We draw pictures from right to left so that the multiplication is has the same order. And I didn't define all structure maps, but the other ones are actually even easier. And now one needs to check that, for example, this partially defined multiplication is associative, etc. And we prove all this. And so this is a Lie groupoid whose orbit coincides with what we want. And I want to, there's also another statement. The dimension of this Lie groupoid, which is 32, is the minimal one. If you have any other Lie groupoid with the same foliation, you get at least 32 dimensions. And I want to just look out 3 aspects of the proof. Like the associativity of the multiplication follows from the not obvious multiplicativity of this lambda. So given the definition of multiplication we have above, lambda satisfies this very nice property. Using it, then the associativity of this becomes a triviality. So the main lemma to prove is this here. And then another important point is that the target and the source, they need to be on the same leaf of this octonionic Hopf foliation. Certainly for x and y equals 0, we see this is 0, 0, and this is also 0, 0. So they are the same. So we can assume that x, y are not 0, 0. And let us assume for simplicity here that both x and y are non-zero. And we want to show, let us not look at the g here. Let us look just at the part this here and this here. And the first thing we want to show is that x, y, and this together with this, they are in the same line. They have the same slope. And a line is a vector space, so we can add it and get another element in the line. And I will prove this in a second. And then you can do the same thing for g. So you can add them and you're in the same line. But now the norm changed. The norm of x, y, this is a different norm. So you need to divide by something and to bring it back to the right norm of x and y. And that's the origin of this lambda. Okay, but let us first see why these are the same slopes. So let us calculate the slope of x, y. Recall that y was equal to m times x. So if y is m times x, and I multiply from the right with x inverse. Now, in general, this is not associative. But however, if I have x and x here, or x and x inverse, it is. That's the fact, because the associator in the octonions is alternative, so it means completely antisymmetric. So now here, this is x bar essentially, which is more or less the same as x, and then the associator is 0 here. So we get this is 1, so we get m. And the inverse is just x bar divided by the norm of x squared, because if you multiply from left or right with x, this becomes 1. So now let us do the same. Let's calculate the slope of this. So we take again the y element and multiply it from the right with the inverse of this one. So now we need to be careful with octonionic multiplication, but it all works out. So here didn't do anything. The inverse, as before, is just the bar of this one. So it's a real number times f bar divided by the norm squared of this, so which is what it's written here. Now you see that first of all, the x square here and the x4, they give an x square over here, so this gives that. And here I get f times f bar, which is also an f squared. So this cancels, and this was just x inverse. So we get y times x inverse. So this means that this is in the same line. And then also we can do the same of g, and we get that the target is in the same line. Now, dividing by lambda brings it back to the same sphere, but the intersection of a sphere and the line is precisely the leaf. So S of g and T of g are in the same leaf. And we can show it's surjective and spans everything. The other thing is we want to show that we get this maximal singular foliation. And for this, we construct a Lie algebroid of this groupoid, which has rank 16. And we get the wished for statement. And now one uses what we had before implicitly with this Maclaurin program proven, that this was an exact sequence on the level of except a resolution of the single foliation. So so exact here everywhere, and it's minimal at the origin. So all the generators at 0, like the boundary maps at 0 vanish, And that gives us that the Lie algebraic rank around 0, 0 always has to be at least 6 or at least 16. And so since the base has also dimension 16 and every Lie groupoid has a Lie algebroid, we get this. I have, like in the last minute, I have 2 remarks here. First, one is that we also constructed on this resolution a Lie 3 algebroid, which is representative of the universal Lie infinity algebroid, which however has no 3 bracket here, so it's a DG Lie algebroid, only 2 brackets and they're differential compatible. And all these things we constructed, like the groupoid, they are G2 invariant, equivalent. So G2 is the symmetry group of octonions, and everything was formulated in the octonionic product. So you see that the groupoid, all the structure maps are equivariant with respect to this symmetry group. And now we have the last question, A3. So Q3 was, given that we have a G SRF or an M SRF, can we prove it's not Morita equivalent to a homogeneous one? So we don't have an M SRF, at least in a real analytic setting. For this, it's an open problem as mentioned. But we can look at the geometric singular Riemannian. There we have a theorem to can prove it's not only not generated by isomorphy as it stands, it cannot be Morita equivalent to one of the isometries. So everything is good except that we don't have an MSRF, but we got like several side effects, like that we can have a first example where a GSRF is not an MSRF in the real analytic setting. And so this finishes my talk. Thank you.
Many on the way.
So I have a few questions, but about your last example, I guess the holonomic groupoids for this foliation, this particular singular foliation, have been computed, right? They're probably known in the literature. Am I correct?
I don't know. Hadi, do you know? Hadi?
Yeah, sorry.
Yeah, do you
Yeah, I mean, there is a way to construct them using bisections for every singular foliation.
Mm-hmm.
And the result is what we know is that it's not necessarily a Lie groupoid. It's sometimes far from being smooth, but it's a smooth along the leaves. That's what we know.
Mm-hmm.
But the construction there is not really straightforward to use and construct it, to compute it for examples. That's the same for the universal Lie infinity algebroid. We know about its existence and its properties, but even for simple examples, it's not easy to construct it.
Yeah, this was quite some work, by the way. Yeah.
So in this, even in this octonionic foliation case, they have not been computed.
Not even here, yeah.
Yeah. Okay. Thanks. Mm-hmm. And may I also ask, in your general formulation of this generalized gauging of the sigma model with foliations,
Mm-hmm.
what confuses me a little bit is that, yeah, at the very beginning, you somehow have two structures which you treated as separate or independent. So one of them is a structure of a Lie module, right, over some basic commutative ring of functions. You took initially C infinity. Okay.
Yeah.
There's another structure which comes from a connection of on your Lie algebraic in one of your formulations.
Yes, in this
I
one.
guess that they combine. I would expect that you can somehow combine them together in something like a differential Lie algebroid or differential graded Lie algebroid, maybe.
Okay, so first of all,
Is it possible?
they both together give rise to this equivariant derivative. So it's a covariant derivative where you can differentiate along sections of this almost Lie algebroid.
And it doesn't square to 0, right? So in some sense, this is a curved structure.
Oh, it's a good question. And then, however, there's another thing. So if we assume that this is a Lie algebroid, so we strict to that case, then we extended this theory for Lexicotov to a deformation. So by adding a kinetic term for the Young-Mills field for the connection A, so something with dA squared. And there you get additional, from gauge invariance, you get additional compatibility conditions. In particular, you get a compatibility between nabla, the connection on E, on this Lie algebroid, with the Lie algebroid structure, which can be expressed in the vanishing of some tensor, and can be expressed also by saying a connection gives a splitting of the sequence from J1 of the Lie algebroid to the first chat of the Lie algebroid to the Lie algebroid. And the first chat of a Lie algebroid is again a Lie algebroid. And this splitting, this connection must be a Lie algebroid morphism. So that is the compatibility one finds from gauge invariance there. So one does find additional compatibilities if one wants to lift it to kinetic terms of the gauge field A.
Is there a way, I mean, I guess this can be somehow reformulated or maybe even simplified somehow by doing a parity change, going to super geometric interpretation? Do you get any mileage by trying that?
Yeah, yeah. We with Alexei Kotov, we also think about this, and we did some work which is actually not published even. Yeah.
And my final question, sorry for having so many questions, it's somehow related to something that I'm working on with Carlos Shabazi, that's why. Have you thought about extending this to gauge supergravity? Because in a way, that's the next step for a physicist, like gauging the n equal 1 supergravity. So you have to also consider fermions and all that stuff.
It's on my agenda, but I haven't.
You haven't. Okay. Thank you. Thank you. Sorry for asking too many questions.
Oh, no, thank you. Thanks for the questions.
Okay, so I suppose we have finished for today. Thank you very much for your lecture, and thank you all listening here and somewhere in the cyberspace. I'm stopping the recording. I'm stopping the Zoom connection.